transmission line is as simple as the piece of equipment that you use to get your signal from where it's generated, that is in your transmitter or transceiver, to where it's hopefully all going, and that is your antenna. And many times where the signal is generated and where you want it to go, where the antenna is located, are very different places. In your handheld units, there essentially is no transmission line because the antenna is a part mounted right on the transceiver itself. But in most cases, very often, you'll need a transmission line. So, hence the subject of tonight's conversation. I'll let it up here for a second. There are two general classes of transmission lines in existence in communications these days. The ones we as hams deal with more often than not are in the first category, and those categories being the lines that are essentially conductors, being coax and balance line, ladder line, if you will. Twin lead is another form of that. And that's the first class, where wires are actually used to carry the signal from point A to point B. The second class, which some of you I know have some experience with, is waveguide. And waveguide is used primarily at microwave frequencies, even though it could be used at other frequencies, the problem being that it gets so large it's impractical. But it behaves much like an antenna, or a series of antennas, if you will, to transfer the signal from point A to point B. And again, it's something that, until you get into microwave work, you don't find very much waveguide. So we'll be talking tonight about the very common types of transmission line that hams use, being coaxial cable and parallel wire lines, into which ladder line and twin lead both fall into that category. The one thing that comes to mind first, I think, when people talk about transmission lines is its impedance. And as most of you know, the impedance at the output of your transmitter is most likely 50 ohms. So you want to use a line that also has a characteristic impedance of 50 ohms. Now, this is kind of an interesting terminology for the lines, in that this impedance is something that exists, but yet in classic terms is a little hard to define. But what it means is, if you had a piece of line, let's say it's coax, and it were infinitely long, that is, it had no end. Of course, we're not going to have a piece of line like that, but if we did, the line would have a characteristic impedance. If we applied AC, a signal of some sort to it, a certain current and voltage would appear on that line, and we could take that current and voltage and say, based on Ohm's law, the impedance of this line appears to be, in this case, 50 ohms, or maybe 75 ohms for some of the other lines that you might run into. And there we get characteristic impedance. Now, if the line is terminated, that is, on the other end there is an antenna or a load that is also of that impedance, say 50 ohms, then the system is perfect, and all of the power from your transmitter is absorbed by your antenna. I'll let it drop for a minute. That's a situation we'd like to achieve. We'd like to have a transmitter of, say, 50 ohms looking into a transmission line of 50 ohms looking at an antenna of 50 ohms. Now, in real life, we don't always achieve that. So we end up with something called reflected power, viswar, standing wave. Those terms, although not synonymous, are generally in the vernacular, like Scotch tape and some other things, used to mean the same thing. Now, standing wave, or viswar, or reflected. And I think I'll use the term reflected power because it is more exactly what's going on. Remember, we said if we had a load that perfectly matched both the signal generator, the transmitter, and the line, that it would accept all of the power coming down that line, absorb it, or in the case of an antenna, radiate it to do some useful work. If it does not match that impedance exactly, some of the power that is sent toward it will be reflected back toward the transmitter. Hence, we have a reflected power coming back in a reverse direction down the line from the power that the transmitter generated. This creates something called a standing wave, and VISWAR is voltage standing wave ratio. So the standing wave, which is actually something we like to have in an antenna, is going to be coming back down the transmission line, and we don't like to have standing waves on the transmission line, at least not much of one. The reason we don't like to have that is because the standing wave can create a voltage that is much greater than what was given to the line by the transmitter. And it can create a current that is much greater at parts of the line than was sent out by the transmitter. What this can do in the most extreme of cases is burn up the line, because that voltage is greater than what the line was designed to accept, and the current is greater than the wires in the line can carry. We try to get this VISWAR, or reflected power, to the minimum by tuning the antenna so that it looks to the transmission line like a very good load. Can we ever get it to an exactly perfect match? Well, really we can't. We can get very, very close, down to where in some commercial circles, in broadcast circles, we try to get our antennas to a standing wave ratio of 1.05 to 1, and I'll explain what that is in a moment after we let the repeater pause for anybody that might have traffic in here.
I'd like to make one little comment before you go any further, Lloyd.
Questions are accepted.
When you have two wires, question and answer period will start after Lloyd's done with his presentation. Pull them together, as you refer to it as a transmission line. The way, in other words, what I'm saying is, this thing does not transmit. The signals cancel each other. That's the main point of a transmission line. It transmits power from one end of it to the other, and during this transmission, when you have two, I don't care whether it's a twisted pair or a open wire feeder or a coaxial line. These two wires, all they're doing is transmitting power, and they're canceling each other. It cannot behave like an antenna. It's not going to radiate off the transmission line. That's the only thing I wanted to say. Thank you.
Can we hold the question and answers until the question and answer period of the program after the program, please?
Okay, we'll do that, and that's something I was going to come to, exactly that point. A matter of fact, if you have a standing wave on the line, it very likely is radiating, and that's something we don't want to happen, and we'll talk about that in a minute. I'm going to briefly describe what the standing wave ratio is and a way that you can figure out what your standing wave ratio is likely to be if you know the characteristic impedance of your source and your load. Source being a transmitter, and we'll say it's 50 ohms, in most cases it is, and the antenna. Now, that may take a measurement, or you may be able to guess, or you may be able to tell what your antenna is if you can measure the standing wave ratio. It's very simply the transmitter impedance, 50 ohms, divided by the antenna impedance, or the lower number, whichever is the case. The antenna impedance is, say, 25 ohms. The number is 2. 50 divided by 25 is 2. Your standing wave ratio is 2 to 1. If the antenna were 100 ohms, the same would be true. You would be flipping that equation over and dividing 100 by 50. The standing wave ratio has to be a number greater than 1, because 1 is a perfect match. 50 to 50 is 1. You see this expressed as a standing wave ratio of 1 point something, 1.1 to 1, let's say. That's the same thing as 1.1 in mathematical terms, and I really don't want to get too terribly involved in the mathematics because I find it very hard to explain it without having a chalkboard, something to write on. But at any rate, we can talk a little bit more about that as we get down the line. Now, if you have a standing wave on the line, all of a sudden something is a little bit off-kilter of what it's supposed to be. And in the case of a balanced line, like John was talking about, where you have two wires parallel to each other, they should be carrying equal and opposite currents. One going up, let's say, toward the antenna. That's positive, we'll call it. Down the other wire is an equal but opposite amount of current coming in. If you let the line radiate, a couple of things happen. One is that the transmission line begins to affect the way the antenna itself is performing. The pattern of your antenna may very well change. In other words, if you're expecting it to, if it's a dipole up quarter wavelength or better, you kind of expect it to radiate broadside to the dipole. If it's running north and south, you'd expect to have a pretty good signal east and west. But the feed line can change some of that, so you've got to watch out for those kind of things, lest your antenna pattern be a little bit different. The other thing you don't want to happen is to have this radiation inside your ham shack. It's not good for you. It probably is going to disrupt somebody on your on your television or stereo or something like that, and it's just not the best thing to have happening. Ideally, you'd like to have the transmission line be just simply that, a way to transmit the power from point A to point B, and not modify it in any way, shape, or form. Okay. Jim, what did we miss on that? Say timed it out.
Roger, timed out or dropped out or something, or maybe it was on my end. I don't know. Ask everybody else what they missed. I was busy doing the counting and up and figuring out the paperwork on this. What did you guys miss?
It wasn't off very long, just 2 or 3 words. I turned it over to direct and really didn't miss anything.
Okay, not saying anything then. All right. Let's talk about the most common kind of transmission line you'd probably be using. That is coaxial cable. Now, in coaxial cable, you know, we've talked about the equal and opposite lines. It's a little bit different in coaxial cable. The outside of the coaxial cable should be at ground most of the time. Now, ground is carrying a current, mind you, but it's a little bit different than in the balanced wire kind of feeder. But this is the most common thing you'll be having as a coaxial line. The center conductor is carrying the bulk of the current that is going to the antenna. Near the antenna, you do not want the coaxial line to be carrying much, if any, current. That, again, alters your antenna pattern. There are several kinds of coaxial cables, or coax, that you'll run into. You've heard the RG types, RG58, RG8, RG59, those kinds of numbers. The RG numbers come from a standard that was set a long time ago when coaxial cable was being first developed and manufactured, mostly for military standards that specified a type of cable, and it said an RG8 type cable will have these certain characteristics. The RG8 cable, which is one I think you probably run into quite a bit in ham radio, is a 50 ohm cable. It's about a ½ inch in diameter, and it's characterized as being a coax in that it has an inner conductor that is surrounded by an insulating material of some sort. It might be polyethylene, it might be a foam, it's generally some sort of plastic, and an outer conductor, which is a braided shield wrapped around this center conductor and plastic piece, and they become coaxial. In other words, the axis of the two conductors is the same, coaxial. That's where it's got its name. RG8 is a fairly good cable. It'll handle power in excess of a kilowatt if there is not a lot of standing wave. It has relatively good loss characteristics for VHF work. And in general, it's probably the cable you would want to use most often if your line is very long at all. Now, at HF frequencies up to about 30 megahertz, where we're dealing with those kind of frequencies, and you're running fairly low power, there are a couple of other cables that you might want to use for short runs. I generally say short runs are around 50 or 60